Good morning, everyone. I'm Andy Cohen. I am the director of the Institute for Advanced Study at HKUST. It's my great privilege to welcome you all to today's roundtable. We are delighted to have three very distinguished scholars with us. Professor Harry SHUM, who is one of our own, an IAS professor at large, along with Ima and Doris TSAO, both from UC Berkeley. The three of them have recently put out a very interesting publication, and since Harry is currently in Hong Kong, we thought this was an opportune time to have a conversation around many of the profound issues that they've raised in their recent paper. So the format for today, I will first turn things over to Harry to give a few minutes of introduction, and then Professor Ma will give a short, maybe half-hour presentation on the work. And then we're going to open it up to a discussion, which I will moderate between Harry, E, and Doris. And we'll just see where the conversation goes. We'll take some questions from the audience as well. So with that, welcome again. I hope that it will be very interesting today. And I'll turn it over to Harry.
Well, thank you very much, Andy. It's great to be back to IAS. Today is really my great pleasure and the privilege to have Ima and Doris to join this roundtable discussing. As you can see, I take this talk very seriously. I dressed up for Yi and with my suit. They usually don't do that at Berkeley. So I actually put together a few slides, if I may get my slides. I just want to set the context that, can you get to the first slide? Yeah. Basically, today we actually talk something related with deep learning. And Yi and I have been talking about, 10 years later since deep learning got popular, what happened, what's happening, what should happen next. I want to just provide a little bit of history, of course, in a very biased view from myself, especially related to some excellent work at the Microsoft Research. I was familiar. Deep learning
Harry,
now
just double check. We are not able to see your slides online.
You are not able to see my slides? Okay. Let me know if you can see it.
Yes, we can now.
Okay, great. So I was just saying that, let me just provide a very brief, view, history of what happened. Of course, deep learning now is taking the world by storm, evidenced by 2018 Turing Awards, three winners, LeCun in computer vision and the image processing, and Hinton in speech, and Banjo on natural language. Clearly that they have done this amazing work. They deserve this Turing Awards. A lot of people don't know that the first real deep neural net for speech recognition breakthrough was done when Hinton was doing sabbatical with Dr. Li Deng at the Microsoft Research in Redmond. Really excellent piece of work in the computer vision side was done by Dr. Jian Sang and his team at the Microsoft Research Asia in Beijing called ResNet. If you do computer vision, it's all ResNet there. So I'm just going to mention these two pieces of work I was familiar with. I already mentioned about that. Was the 2012 paper, by Hinton, and then and also the 2015 paper was excellent engineering work, and they were able to train up to 1,000 layers of deep neural nets. But what's really important for us to really look at, why today deep learning and AI is so hot. The public, the general public just got fascinated, I think, thanks to a few breakthrough systems that we have seen in the last 10 years, especially AlphaGo for people here in Asia who play Go seriously. I thought it was heartbreaking to see that AI can beat our national champion easily. So that was really stunning. Of course, recently AlphaFold, also just to provide even more imagination for people. What can we do now? We can actually see a lot of protein structures discovered by AI. I also want to bring up this recent work by DALL-E by OpenAI. That's also fascinating. That what you can really do with the text and the image I think it provides new tools for artists as well. So we all know that why deep learning worked well. You will get into the details mathematically. What really happens. By and large, three things converged. The more and more data, amazing amount of data, especially with the internet, and the huge amount of computing power. Moore's law is not completely dead yet. Then, of course, we have all those clever algorithms, including many by Yi and his students. I really want to mention that along the way of AI deep learning revolution, the company who really led the way and benefited tremendously is NVIDIA. They're selling GPUs like crazy, and I'm sure Jensen always laughing all the way to his bank. So I do want to mention about the opportunity we actually have in academia about AI for science. If you look at what's really happening here is AI is really a tool. It can help many different subjects. In mathematics, you can use AI to amplify mathematicians' intuitions. Previously, we could only try a few different scenarios. Now AI can help you to go to thousands, if not millions of scenarios. AI for physics, and I have been talking to Andy here in IAS. I'm personally very interested in AI for astronomy. I think a lot of interesting problems there. Perhaps right now is the most exciting thing happening in our field is AI for biology and chemistry, especially with applications to drug discovery. It's also something I'm trying to promote here in Hong Kong to our chief executive and other government officials. I think in Hong Kong, we actually have some opportunity to do something in this particular field. Finally, I want to mention that as a computer scientist, I thought it was really fascinating how deep learning has been bringing down the barriers across disciplines, like natural language and the computer vision used to be so far apart. Now you can actually do things quickly together. Of course, Yi and I have been talking about the really close the loop for vision and the graphics. Finally, I want to just finish my introduction by really setting the stage up for Yi and also Doris. That is really in the last couple of years, I have had the opportunities to work with Yi and together with our students have been really thinking about this important notion of intelligence. It's not only just artificial intelligence, it's also human intelligence. The last couple of months, we had the opportunity to work very closely with Doris, which is really a blast. It's amazing to hear the very interesting views from top neuroscientists like Doris. How should we really think about intelligence? Turing criteria is no longer really appropriate at this stage as a test for intelligence. So how did intelligence emerge? There must be some kind of guiding principles. So that led to this paper that we recently published. With that, I'm going to pass it to Yi, and Yi is going to give us a short talk in 30 minutes or 35 minutes. Yi.
Yeah, thanks for the Institute of Advanced Study for having us, and also, also Harry just give a very general background of what happened in the past 10 years, right? The revival of deep networks has really generated all kinds of excitement and promise for artificial intelligence, a lot of excitement and around this topic. That is and a success as well. So there are actually two things that two main things we're trying to understand, right? After this is about 10 years mark. On one hand, we really wanted to understand what the success of artificial intelligence in the past 10 years. Meaning, what is really the true reason behind it, or what actually have done, right? Another thing is obviously a very bigger question is that how is the practice of artificial intelligence, the modern days, are truly related to the word intelligence, right? And especially we mean natural intelligence. How much that they're the same, how much they're the different, right? So, this is also the question has, really intrigued me for the past, 10 years. And also in recent couple of years has been working with also Harry along, try to understand deep learning or learning, or understand artificial intelligence or intelligence, right? So this is some of our, at least some of our findings, views we can share with people. Obviously, Harry gave us history about what happened in the past recent 10 years, right? The deep learning has been able to bring down barriers. And in computer science, I wanted to argue, right? In fact, it has helped to bring down barriers in the robotic scope, especially in the ECS. Many different sub-areas are brought together. If we take the view, deep networks brought down sub-areas in computer science, we can argue maybe the study of the intelligence is going to bring down many more sub-areas, because this is a time where it requires integrations. It requires understanding many pieces together, right? So I'll start with, so this, our paper also try to have this more general setting, but it's a position paper, it's a review paper. But any position reviews, we cannot be as convincing if we don't even have any evidentiary support, right? So I'll focus my study with my expertise, right? I study computer vision, image processing. So we'll try to use the problem of modeling visual data, right? Providing you some evidences and how we can approach the visual data modeling, and maybe that give us some ways to look into more general principles behind the learning or intelligence in general. So our inquiry, of course, started with trying to understand deep learning, right? This is actually my journey for this actually started 6-7 years ago. Got more serious, especially after our colleagues at Microsoft Research has invented the ResNet, has really boosted the performance, and all the practice has become mainstream. So that's the time we try to understand deep learning, try to understand what's going on. So my journey actually started with interest in deep learning, and suddenly realized that maybe the correct answer to understand deep learning or deep networks is probably trying to understand what the learning is all about, right? Maybe deep networks are, for many years, I have studied the deep networks as the objects itself, right? What is the properties of networks? What are the phenomena? How can you use some of the analysis to explain, understand some of the phenomena generated by deep networks? But after a while, I think that's not really enough, right? I start to realize that maybe deep networks just a means to the end. The reason we have our brain, the reason we have deep network, maybe they're just tools to achieve something. But if we can understand that objective, maybe we'll be much better off understanding all the so-called mysteries around deep networks. So that is, we start with try to set from sort of first principle, what really learning from data is all about, right? And this is, of course, you can see Harry gave very impressive systems, right? Like DALL-E or, be able to generate the images and so on and so forth. But there's a separation between those are the so-called artificial intelligence, right? That maybe not all intelligence is about, right? For example, for generating images, maybe it's enough for the machines to learn certain distribution of the data, visual data, right? So that you can regenerate the data, you can sample it. To have very impressive, right, resampling capabilities. But is that really intelligence, right? What's beyond that? Maybe intelligence is not just all about the learning the distribution, but also about the organizing information, right? Make it simple and so on. So realizing that, we started realizing that maybe the learning is not just to learn the distribution of the data, right? Our brain or any intelligent beings or future intelligent systems, robots, and probably we need to organize the information to our benefits, making inference, predictions, generations much, much more efficient, simple, right? Become memory, things we can easily use in the future, right? So that leads to the sort of principle we call the parsimony, right? The sort of try to answer the question, what is learning trying to do? The objectives of learning. Right? Not just learn the distribution, not just compress the data, but also organize them well. If that is our goal, if we're clear about our goal, right, then the next question, obviously, how do I achieve it? What are the efficient, effective computational mechanism or algorithm or means for me to achieve that goal consistently, right? So this actually naturally brought us to, so just like I gave a very simple example, right? If I wanted the room temperature to be 75 degrees, right? So we all know, the modern engineering model is that you have a very simple control system, the air conditioning, right? If the temperature is high, you blast cold air. If the temperature is low, you bring in warm air. So you correct that error. So this is actually a very universal mechanism, right? People discover, actually also from nature, right, that the so-called closed loop control system. Closed loop system is always used to using feedback to correct the error if we are initially learned models, initially learned predictions are wrong, right? So this is actually this start to realize then that maybe a best, most effective way of learning is actually through such a closed loop control system to achieve that this the objective of learning. Okay? So that's actually sort of a connection to deep learning. And then let's just start with the goal we try to set out to do, right? Again, we try to bring back, there's a lot of phenomena, a lot of practical settings, many tasks, right? So one of the things to try to study approaching something in a more principled way or more fundamental way is that try to make minimal assumptions about, right? So here, basically we make it most simple, arguably the correct assumptions about the real world data is that we're dealing with the real world data like images or audios, speeches are very high dimensional data, right? Each image has millions of pixels. And of course, the data belongs to multiple categories, right? Tens of thousands of class of objects, categories. We can actually assume, of course, each class, the image associated with each class has its own structure. What make apple, apple, right? So you can think about the image belongs to each category. Maybe in a very high dimensional space, D could be millions of pixels. It just lies on some low dimensional distributions with low dimensional support. We call them manifolds, right? For example, all the image of apples lies on this red curve, right? Of course, this is illustrating the low dimensional structure. Could be multi-dimensional, right? This curve could be 5-dimensional surface in a million dimensional spaces. So this is what we face, right? Our brain face this kind of data. We get blasted by this kind of data every second, every minute, 24 hours, right? So our brains try to make sense of them, try to sort them out, right? Hence, this tremendous amount of data, we have a very limited capacity, right? One natural assumption is that what is the function of our brain, or what's the function of any intelligent system? Is that facing such realistic data, we really try to map them to find from such real data, map them to find a very compact and structured representation of the data internally. Of course, 10 years ago, right, deep networks actually stumble upon something quite simple, right? It's just that if I only care about the class of the data, if I have, let's say, 3 classes, I just map them each one to its own class. I'm representing the class as a one-dimensional vector, one hot vector, 1, 0, 0, 0, right? And I can actually model this mapping with the deep networks, right? And also through training, through supervised training or backpropagation, I try to tune the parameter of the network such that the output of the network are most correlated with such a one hot label, right? This logics of this output this is called cross entropy, right? Minimizing this what allows the output of the network match the best with the class label. This actually generated tremendous success, right? All this, initial AlexNet and later on ResNet and so on and so forth, many other networks realize this actually can get very good performance for classification. Obviously, there's also a problem associated with this, right? There's all kinds of caveats associated. May not be very robust, may not be very robust. Also, that the traditional network actually can fit anything if the network is chosen to be too powerful, right? And you can randomly pick class for every single image, but the network still can fit it. Also, that you kind of get what you reward, right? So the network eventually, since you are asking the output of the network to match the class label, hence there's a phenomenon called the neural collapse that all the features that you learned towards the end of the network, they start to converge in one-dimensional, right? Which kind of expected, right? This is called the neural collapse phenomenon. Now, for the many tasks, right, we don't just care about the class label. What if, I just don't want to know this is the image of Apple. I want to know what makes Apple different from oranges. I want to know all the characteristics of Apple, right? Let alone some computers are called apples too, right? So the class label really carries very minimal information about it. It's high-level semantic, but doesn't really correspond to very well with the structure of the data. What if I also want you to draw me an apple, right? Just like a DALL-E does, right? To produce an apple instance, if you want to convince me this is apple, just show me what an apple looks like, right? Then this is the question: is that in the sense that we don't just want to map separate different class, right? Data lies on those different surfaces to the one hot. Maybe we want to map each surface to a low-dimensional subspaces, and the dimension of the subspace is just matched with the distribution, right? The original degree of freedom of the data, right? So we want to map X to some feature space Z, representation space Z, such that we can also recover the original data from such a compact representation, right? This makes this process sort of invertible, right? Sort of auto-encoding. There's many, many different names for this, right? And we want to have this kind of representation. We want to map the high dimensional data to a very low dimensional data, capital D to lower d, as well as the original data might be nonlinear. We want to make sure that the structure in the hidden space is linear, right? It's very easy, compact to use, and also incoherent. And also we want this data, the representation, to be information preserving or faithful, right? Preserving all the information we want of the original data. Of course, subject to some precision. Now, let's try to be more formal, right? So this is to try to, if this is our goal, we want our data, we try to learn two mappings, for example, from the data to the feature space through a mapping F. Of course, the inverse map, we call it G, right? A generator stands for generator. We want F and G satisfy certain conditions, right? The formal auto-encoding. The map data from one surfaces to the feature subspaces, and then back to the same surface, right? The formal auto-encoding. Now, as long as you realize this, if this is what you want to do, you start to realize that there's something not so comfortable, right? For example, you do not know the distribution of the data. You do not know the dimension of each category, right? Apple, orange, what is the dimension? But you know they're low dimensional. Maybe that's what you can assume. And for that, also, if you want in the feature space to separate, make sure that the subspace or feature associated with Apple are different from the feature associated with oranges, you need to give the feature space needs to be large enough, right? The feature space needs to be at least as large as the sum of all those intrinsic degree of freedoms. If that is the case, right, everything we do here is deductive, right? So if that is the case, then the feature associated with Apple becomes a low-dimensional surface or subspace inside the feature space. It becomes hidden, right? If you're not careful, you don't even know where the Apple features are, right? That's why this in this case, right, in machine learning, people learn generative model. They call those models hidden, latent, right? Because even in the feature spaces, you may not necessarily know where distribution is of the data. So of course, to resolve this difficulty, right? In our brain, we cannot have such a hidden representation, right? Every time we think about Apple, our brain knows exactly where to go for it, right? Hence, we know that the information must be organized, right? It cannot be hidden, and you can only access through random sampling, right? So hence, the representation for the data needs to be highly compact and also organized, right? Make them linear subspaces, for example, and make different categories, even orthogonal subspaces, right? So that I can represent in different categories of objects with a different set of neurons. They don't have to interfere with each other. We call it disentanglement. Now, if this is the case, right, you start to suddenly realize that there is nothing new at all about learning, right? Because we have been doing this for hundreds of years. in computation, in computer science, in electrical engineering, in signal processing, in pattern recognition, in statistics, right? So everybody familiar with PCA or SVD, right? So this is exactly the same problem conceptually, right? We have data lies on high-dimensional spaces, but we make the simplified assumption that data lies on the low-dimensional subspace, a linear space, right? Then we try to project the data to a lower dimensional space, then we try to lift it back. If this projection preserve all the important information, we should be able to lift it back to regenerate the data. This is exactly PCA, right? And of course, this is too ideal, right? Although this is very important, most basic models in statistics, but it's maybe too ideal for real-world data. Right? Real-world data could be multi-model, multi-class, right? They could lie on multiple subspaces, multi-mode. Then in this case, this is what we call the generalized PCA. There are multiple subspaces to model my data. Also, even multiple subspaces may be still very limiting, right? You assume essentially that locally the data is linear, the structure is linear. That may be too good to be true, right? The real data maybe lies on some low-dimensional, nonlinear surface, right? Hence, our goal becoming that if that's the case, we try to linearize that surface, make it a linear subspace, right? Make it flat, so that it's much easier to record, store, interpolation, extrapolation. Everything becomes easier, right? So we have then, because the data is, if it's nonlinear, we have to find a nonlinear mapping, right? And also have to lift it back, right? This actually is called a nonlinear PCA. In fact, this is the origin of autoencoding, right? The first paper is called precisely use neural networks to achieve this task, 1991. Actually, in 1993, Hinton called this autoencoding, gave the name autoencoding. Now, so you can actually see conceptually, all three categories of problem are very similar to what we set out to do, right? We are trying to do. Only that they're a little bit too academic, too idealistic, right? The real world scenario we're dealing with today, the bottom precisely maybe is the bottom case. We have data from many, many categories. Each category is a low dimensional distribution or submanifold. We try to linearize them. Map them, linearize them, map them to low-dimensional subspaces in a very compact form, and also we make sure this mapping is faithful. Now, how do we do this, right? If we believe this is what the deep networks, all the learning is all about, then how do we approach it? How can we even, if we understand this, we can even understand what we have been done in the past 10 years. Maybe we can draw some inspiration, right? This is how we approach a very complicated problem, is we through a very simple problem. That's why maybe those simple cases were introduced first, right? So maybe we can also learn something from them, right? How can we solve the linear cases, right? From X to Z to X, right? In this case, we know since the original data is linear, it lies on already on the linear subspaces, right? The mapping can be linear. We're looking for a matrix, right? Project the data to a low-dimensional space, and we lift it back. Again, to make sure this projection preserving the data, right? We make sure the X hat is recovered. After projection and the lifting, the recovered X hat is very close to X through L2 norm. Maybe the Euclidean distance are close, right? So everybody knows the solution. This is precisely principal component analysis. The almost near closed form solution is by singular value decomposition, right? Now, the problem gets a little bit complicated. If you have a nonlinear structure, if your data is nonlinear, right? Assume a single nonlinear structure, right? So then the mapping has to be nonlinear mapping. Cannot be linear anymore if you want the result to be linear, right? But we don't know the original submanifold. So in general, we don't know what the F we should use. Of course, these days, everybody can wave their hands and say, let's just use some neural networks. Fine. But you still have to explain it. Why it is adequate, which neural networks, right? Then, of course, after we have the feature, we can learn a generator, go back to the data. That's what all this, generative model is doing. Now, obviously, we can emulating what we do with the PCA case. We just want to make sure the recovered data to be close to X, right? So this seems that we're just emulating what we do in the linear case, but there's two difficulties, right? As I mentioned, one, we don't know what F and G. But this may not be the hardest problem, right? Because at least I can try with networks. Well, the hardest problem actually is what is the distance you use between X and X hat in the nonlinear case, right? The image processing computer vision spent nearly 40, 30 years trying to understand what is the right distance between two images so that they are similar. The original Euclidean distance is actually wrong, right? Because if the same image, if I shifted it to the left by a few pixels, it's the same image. But the L2 distance can be very, very different, right? And if the same image, if I just blur it, right, it looks very, very different. But the L2 distance is very close by. Now, what is the distance to use, especially the structure of the data is not clear. It's actually the most baffling problem. Right, of course, then people say, well, if you wanted to measure how close X and X hat is, you have to tell me something about X, right? It cannot be just some arbitrary distributions I know nothing about, right? Try to tell me how maybe lateral image is generated, right? Again, people spend 30 years on this. What is the generative model, statistical generative model, right? David Mumford, the Irv Granander, Song Chun-Zhu spend careers on this, right? What is the generative model for natural images? If we have this generative model, even it's probabilistic one, when we actually calculating the X hat, how likely X hat is a real image through its likelihood, right? This is very plausible thought, right? Also been taught in statistics. Unfortunately, when the image distribution in the high dimensional space is degenerate, those maximum likelihood is intractable to compute, right? Even the likelihood. Not only we need actually the posterior, right? So after a while, people, basically the generative model is very elusive, and also even you have the generative model, you cannot compute against it. Okay, it's computationally intractable. Then what do people do? Let's approximate with some lower bound, right? Variation is very, very popular, right? Gazillions of papers writing about it, right? Let's try to minimize some lower bound. Actually, it turns out that this lower bound is not computable either in most cases, okay? Then what do you have to do? You actually have to make assumptions about what those target surrogates has to be. They have to have certain good structures so that those variational lower bounds become computable. Actually, this is precisely the motivation of the recent more popular diffusion model, right? To make this computable. Now, of course, this is being practiced again and again, and that's why there are thousands of papers. Why? Everybody come up with their own lower bounds or different surrogates approximation, right? And everybody think my approximation is better than yours, at least on this data set. Hence, I'm qualified to publish this paper, right? This will continue forever, right? If we don't settle this, right? So after a while, actually, even people working on the generative model start to give up, right? This is Tu Zuo Wen, right? He's a student of Song Chun-Zhu, the long tradition of people studying generative model for natural images. He said, I gave up, right? So I'm trying to say if we can learn generative model from discriminative approach. That's his 2007 CVPR paper. Of course, later people make this popular through the name GAN, right? It's exactly the same idea, by the way. It's as I said, if I don't know how to measure the distance between the generated, right, decoded image and the real one, maybe I can use neural network to separate them apart, to train a discriminator, right? Try the best to separate them apart. So this naturally leads to a sort of kind of game between the generator and the discriminator. Generator is trying to make sure X hat is close to X. Discriminator is trying to make sure X hat separated those two, right? That leads to sort of a game formulation, right? Through this cross entropy. Turns out mathematically, this is a little bit misleading because this is actually not a game. This is not a real game. It turns out this is a fake game, right? Meaning that you can actually convert naturally to a minimization problem, right? So this problem is mathematically exactly equivalent to minimizing the so-called Jensen-Shannon divergence between the distribution of the real data and the generated data, between X hat and X, right? So again, this seems to be, then people actually celebrate this, right? So if we do this, actually it turns out that if you can minimize the Jensen-Shannon divergence, actually, yes, you can learn any distribution in the world, right? Sounds too good to be true. From a computational perspective, this is indeed the case because the Jensen-Shannon divergence is impossible to compute in the high-dimensional space. Why? Very simple. In high-dimensional spaces, if two distribution has two long overlapping support, the Jensen-Shannon distribution behaves exactly like L0 norm. right? So you can wave your hand. We all know minimizing L0 norm is actually NP hard. Okay? So of course you can see this is kind of tautological, right? Yes, we can learn all the distribution in the world if I can solve NP hard problem. We're done, right? So actually this kind of sentiment gets celebrated in the machine learning literature, right? People are actually saying tautological things, but they're not aware of, right, the computational barriers in front of them. Of course you can approximate, right? Hence, because Jensen-Shannon is very difficult to compute, and people approximate with Earth mover distance, which is also called the Wasserstein distance, right? L1 distance. Sort of approximate L0 norm with L1 norm, right? This is actually not as simple. Turns out in this case, the W1 distance is not computable either. Meaning it's again NP hard to compute for general distributions. It doesn't even have a closed form for Gaussian distributions. Neither is Jensen-Shannon. So which means even you are approximating two Gaussian distributions in high-dimensional spaces, you have to resort to sampling, which is computationally prohibitive. Again, in practice, what people do, let's approximate, right? Again, hundreds of thousands of papers propose a different way to approximate the distance. Also, very powerful computers and large data sets were used to learn those distributions through sampling, very brute force sampling, right? In the end, that's why, right, the performance become an arms race, right? Who has more machines, who has more data, can approximate those things better, hence you win. This is the game academia will for sure to lose, right? Because it only relies on the resource for a very good reason. Of course, for theory people, this is even more troubling. Why? Because it says, oh, everything I do has to be approximated numerically. There's nothing theoretically you can do because there's no closed form. Is the case, has to be the case, right? Keep in mind, guys, right? Nature, our brain, including our brain, let alone zebrafish, right? Nobody knows Jensen-Shannon distance. Nobody knows W distance. Nobody does random sampling. Nobody knows MCMC, right? So how do they compute? They must compute in something very simple, very efficient, and yet very basic, right? Turns out the measure of distance in high-dimensional spaces between two distributions, especially when the distribution has good structure, compact good structure, linear or Gaussian structure, there is a closed form formula, right? Actually, people know this in information theory many, many years ago, right? Since Shannon, right? So how do I measure the distance between two subspaces, for example, right? Very simple, right? So I can fill this two subspace spanning entire space volume. I can fill them with, let's say, blue balls. Sphere pack, how many balls? This space, right? Can give me a sense of what's the total volume. Then if my data lies on the two low-dimensional subspaces, those green area, I can pack them with green balls, much, much less, right? So this is very basic population, right? Just using sphere packing to measure the volume of your space. Then the distance between these two subspaces is just measured by how many blue balls there are, or the whole subtracted parts. That's a natural distance, right? So you can measure, right? If the two subspaces are closer, the space is smaller. If they're separable, their space is larger. And the good thing for Gaussian or subspaces, there is actually closed form formula derived by Shannon for you many years ago, right? We already know the closed form. So hence, maybe what our brain or any intelligent system try to organize your information, maybe you should really maximize this. Because the difference really is corresponding to the so-called information gain. How much you gain by knowing that your data lies down the low-dimensional subspaces versus could be anywhere in the space, total space. This is what we call the maximize this coding rate reduction, right? The number of blue balls, take a log, that's actually the average number of bits you need to code each location of each ball. That's called the coding rate, right? The subtracted parts, that's actually the whole minus the sub parts. We call it the rate reduction. How much coding rate gets reduced by representing your data in this way. So if you do this, if this is something you try to maximize, optimize, something magical happens, right? So if you try to maximize this quantity, the space of blue balls packed in the space between your feature representation, you can take the most naive approach to optimize this. Let's say, for example, let's try to perturb the representation so that the rate reduction gets improved, right? Then you can compute the gradient, do this incrementally by following the gradient of the rate reduction. Then this rate reduction has multiple forms, right? It's the same expression, but you can interpret it in very different ways, right? It has this expression. If you're representing this messy matrix as a linear operator acting on your data from the previous iteration, this exactly become a residual network, right? This optimization algorithm become a residual network, has a structure of this kind. Or if we say, I don't want to do that, I keep all the nonlinearity, right? This is a cubic function, the states from the previous iteration. Then this is exactly the iteration for the transformer, each layer, the attention head. Nothing else, right? So basically, residual networks, transformers, each layer is just basically trying to compress the data or linearize data, maximizing the rate reduction, making the coding more compact, more informative. That's it. If you do this, you actually can derive, this leads to a, forward constructing of the network, forward explainable, right? So you can see that this approach is very, very different, right? It's been 70 years since the deep networks was incepted, right? People come up with idea, right? But the practice has not changed at all for 70 years. It always try to fit the input-output relationship. The architecture is tried and tested, right? And each layer is empirical. People still don't know what the ReLU is doing, right? They're still writing papers about it, or normalization is doing, right? And to achieve invariance, you actually have to go through the augmentation, right? Using CNN, and the initialization is random, and you learn with backpropagation. Even after you have learned, the whole network is still a black box. The representation is still called the hidden and the latent. It's kind of ironic, right? If I spend billions of dollars train a network, I learn a model which is still hidden and latent. Now, in this case, from the compression point of view, right? It's a completely 180-degree reverse, right? The objective is principle, the very basic, bin counting basic, right? We try to maximize the number of spheres packed into the representation, and then each layer is doing iterative optimization, right? Then the operator is doing greedy descent or any function, operational meaning I assign to do it. And also the network is constructed forward fashion. It can be optimized either forward or backward. It's just fine-tuned. After I learned, the network is white box. And also the representation also is white box. Everything is white box. Right? So, but this is one way, right? This is just one way to mapping your data to the representation, right? But don't let me fool, right? These days the machine learning literature can be very, very misleading, right? I intend not to do that, right? So I just told you this rate reduction, right? This formula is closed form if your data distribution or if your feature are subspace or Gaussians, but real data are not, right? Real data is X. It differs from a Gaussian or subspace by a nonlinear mapping F, which I still have to learn, right? Now the question is, this applies to Z, but does not to X hat. What happens? Right? If I want my X hat to be X, the decoded data to be close to the original data, if I want to draw an apple, how do I make sure the apple I draw is close to the original apple? Right? How did we learn that skill? This is actually one of the most profound questions if you think about it, right? This actually has something to do with how can we make learning autonomous? Almost all the practices right now of artificial intelligence so far in the past 10 years are not autonomous. They're all supervised by human. The architecture are decided by human. The reward function are decided by human. Even how good the results are decided by human. but yet natural intelligence are fully autonomous. We don't, for example, DALL-E is great. Why is great? Because we say that's great. But a monkey doesn't have that choice, right? Monkey has to remember what the apple looks like. And also, monkey cannot access, doesn't carry something in his hand to say how the shape of apple, the real apple, is just like what he imagined. Try to compare X and X hat. We never ever do that. We never compare things in the data distribution, in the data space. Everything should be internal, right? So how did we do that? So let's try to restate the problem a little bit, right? We start with data with highly complex, multidimensional. We try to map them to organize the subspaces. And we want to make sure this mapping is exactly auto-encoding. We can map to X to Z, Z go back to X, right? So the question is, but measuring differences in the data space is troublesome, right? Physically impossible, right? Computationally intractable. The why we keep insisting doing it. Nature certainly doesn't do it, right? So how the nature bypass this problem? We believe, right? So you don't, in order to compare X and X hat, you don't have to compare X and X directly in the data space. You compare them in the feature space, in your head. You map the generated data back to your brain again, right? Compare them internally. That actually very magically falls to something very familiar to us, at least for some of us, right? For one sub area, people recognize this is exactly feedback control, right? So if I want to control, remember my example, if I want to control the temperature of a room, right? I couldn't care less how every particle moves in that room. I only have to measure the temperature. I only have my thermostat to check the real temperature and the set temperature if they're the same or not, right? That will be enough for me to guide the air conditioner to work, to set the temperature just right. Hence, this, bring things to closed loop is a natural learning mechanism for us to correct our errors, right? To learn something consistent. Now, hence, just put things together a little bit, right? So the data, we wanted to map the data to organize representation. And if we want to make the representation to be faithful, we want to be able to regenerate original data. But we cannot compare the generated data with the true data. Hence, we map the generated data back to the feature space again, bring everything back to a full closed loop, right? We only measure the difference between the feature of the true data and the feature of the regenerated data. And also because of these cases, right? So the role of this encoder naturally changed, right? F, remember, is the encoder from the visual cortex to from the retina to my brain, right? So it actually also play a role of a sensor, right? If there's any difference between the generated data and the true data, you try to sense it, try to produce error. If the apple you draw, it doesn't look like a real apple, right? Fine. I go deeper to my memory to regenerate, correct that error. Then the decoder actually become a controller, right? The decoder says, if you tell me there's an error, then next time I do better. I try to minimize the error, right? Hence, this is naturally becomes a closed loop feedback control system, right? Then the F, the encoder, really try to tell if there's anything different between the true data I observed and the data I memorized. And if there's any difference, it gets reflected through the internal coding. Then the G will take that, try to do its best to make sure that the regenerated data, the blue curve, chase the true distribution of the data, right? This is a natural pursue evasion game, right? That this is absolutely necessary, actually. If you don't do this, if you just correct the error, actually it turns out there's no way you can guarantee if Z and Z hat are the same, X and X hat would be the same, right? So this is actually something very, very interesting. You realize that everything here is absolutely necessary for the coding decoder work together as mutual critic to each other, so that to make sure the data they observed are precisely memorized correctly, faithfully. Right. So they actually end up with this minimizing, sort of the object function right, put together. Remember, the rate reduction is trying to make sure all the subspaces are different, right? Every class becomes a subspace, different subspaces are mutually orthogonal. And this term is trying to make sure the reproduced data match with the original perceived observed data, right? Hence, the parsimony and the self-consistent gets imposed together in this single bin counting object function. There's nothing heuristic here. This is just counting the bins, counting the balls, right? There's no weights, except the parameter for a network, nothing for you to tune, right? So very simple. Everything is in closed form, right? The closed loop enforces consistency, right? And if you can optimize this, you guarantee that the feature you learn is structured. It's a linear discriminative representation, right? Suddenly you realize a lot of things are gone, right? You don't need to specify any priors anymore. You don't have to guess what the generative model for your data anymore, right? What is the target distribution? Which one is independent of which one? They're all gone. You don't get to decide anything, right? You don't have to measure any distance, come up with any heuristic distance in the data space anymore. And you don't have to approximate all these intractable quantities, KL divergence, maximum likelihood, mutual information, Jensen-Shannon divergence, W distance. You don't need any of them, just like animals, right? Animals don't even know what Gaussian distributions look like, right? Let alone all those fancy distances. Yet, does this work, right? For the last couple of minutes, I'll show very, very quickly. Yes, this actually works. So this is the differentiator. What we are kind of excited about this is that, there's many, many theory in the past 10 years been proposed for explaining deep networks and the deep learning, right? But to my knowledge, few has really impacted how practitioner can guide practitioner to change the practice, right? Or explain the practice to the full extent, right? Here is something, this is a framework naturally works, right? So to make a point, we choose all the publicly available data sets that we can get our hands on or our resource can allow, right? And we choose the simplest network architecture. There's no change adaptive fine-tune any hyperparameters. All the hyperparameters for all the data sets, for all the network are exactly the same. Doesn't matter if the data set is large, small, high resolution, low resolution, we just do the same. Right? So all the experiments, I'll show you, flash you through very quickly, just give you sort of empirical evidence, right? For example, this is on MList, CFAR, ImageNet. Right? Suddenly you can see this very simple closed loop, right? With fair, actually unfair comparison to us. Our network is smaller, right? To GAN, original GAN, or VAE GAN, this is variational autoencoding, right? VAE doesn't work for generative purpose, but you have to add with GAN, right? So regardless, you can see in the first cut, right, the algorithm already gave better qualitative or quantitative results, right? And not only that, it learns more. It doesn't learn a hidden representation, right? We know exactly which category is in the space. It's a subspace, right? So the digits, not only we can reproduce digits, right? And also each digits, we each become a subspace, right? We can fit with the subspace, and we can regenerate the same digits from the same subspace, unlike other conditional info GAN or conditional GAN, right? And it actually has a lot of mix, right? 3 and 5 are mixed, despite all the effort trying to heuristic control independence. Here, we don't do anything, right? The different subspace become a different type, right? And also the network, the representation is both generative and discriminative. We can actually compete on both ends, right? The network, the representation is both can generate original data, also classify different classes. And also you can have different orientation, scale, they all become different principal components. They found different direction of the subspace you fit with the data. It gets learned automatically. You don't get decide anything, right? So this is on CFAR 10, right? 10 class of images, right? So we each row is, so there are 10 classes. So each block is one class, and each row is one direction principal component in one of the subspaces, right? So we sampled along that subspaces, regenerate the data, shows to you. You can see that statistically, right? The appearance looks very, very different. Every principal component are very different. They are all learned automatically. You don't have to decide anything, right? So you can see people in machine learning start arguing that disentanglement is difficult, right? Yes, for human, right? Because you really don't know the data. right? We try to interpret data heuristically, but in this way, the disentanglement becomes very, very easy and natural, right? Because different classes get disentangled as different subspaces. And the different statistical attributes get disentangled as principal component. Nothing more, nothing less. Human, we get to decide nothing. All stipulated by the data structure. If the data has that structure, it will pop out, right? For faces, right? The first principal component between X and you can see is actually the pose, right? The generated data gets aligned perfectly. Also, you can look into the deeper principal components of the face, right? For example, the ninth principal component associated with hair, sunglasses, right? Sunglasses become, or the 23rd becomes associated with the hair or hat. Again, you don't get to decide how many visual attributes there are, but they're independent or not, right? The data stipulates that. The same with, here the principal component is the layout of the room, right? They're all statistical, right? The model learns what you ask them to learn. The ImageNet is the same. I'll just flash them through. I mean, we don't. Again, people say that training train the generative model is very finicky, right? Very fishy. It usually leads to mode collapsing. With a closed loop system, you don't get a collapse, right? We all know the closed loop system is very, very stable, very, very sturdy, right? That's what they're designed for, right? So all intelligent systems, all systems that are alive are closed loop systems, right? So there's probably a very good reason for that, right? So it's very, very universal. We believe this is sort of a universal architecture, right? So map this data with structures, internal low-dimensional structure into something highly organized, compact, right? And the parsimony is really an information theoretical way to characterize how much information in your data. So how to represent it in the best compact way, right? And the self-consistency naturally falls into the realm of control system or game, right? That's the most two universal mechanism, closed loop plus a self-critical game are the two universal mechanisms for us to learn something correctly, to verify what we have learned is correct, it's consistent. And if you do this, the object function is purely white box principled, right? Bin counting, basic. The network architecture is just conducting the compression, optimizing this objective, nothing more, nothing less. And after you're done, the learned representation are also highly structured and they're explicit. They are compact, right? So this actually opens all kinds of questions. I think the roundtable will have time to discuss more broadly, right? Even mathematically, this actually, we barely understand, right? Empirically, this works wonderfully, but we don't understand many of the mathematical problems behind it. When this converge, what is the property of this? One can guarantee certain things, right? The only case we can prove is a very simple case when the data is original, is already subspaces, linear subspaces, the GPCA type of setting. We can prove this method does work, give the correct solutions. But beyond that, for some manifolds, we don't know, right? And also there's many, many engineers, right? So things like that, how do this generally works in more broader settings? For example, in the nature, right? We don't learn this for 10 classes all the time, or together, right? We learn things incrementally. We learn one English words at a time, right? So it turns out that this closed loop, but we all know in the past, if you train neural network, the open loop neural network, it has this phenomenon called the catastrophic forgetting, right? If you learn 10 classes, you ask to learn 3 more new classes. What you have learned in the past 10 classes will get forgotten. A closed loop system do not forget at all, right? So it turns out that this closed loop can learn things in the one class at a time.
How about we just wrap it up?
Yeah, okay. So also you can learn in a totally, one sample at a time, right? Works in a totally unsupervised setting, one sample at a time, right? You can learn much, much better representation, right? And hopefully this kind of things we learned sort of, resonate with a lot of the phenomena we start to observe, right? In the monkey or in primate brain, with, different areas coding different types of objects and so on, right? So this is kind of the references. I'll just wrap it up. I just, end at this slide. I think it's very important, right? And about 70 years ago, Wiener wrote a book about cybernetics. He precisely take the view that we need to look at intelligence as a system, not components. not segments, not isolated component, right? He already mentioned compact coding for information, closed loop feedback, game, white box modeling, handling nonlinearity are the key to understand the brain, at least the signal level. Right? So I hope this, give you a little bit overview of what, we bring back to the roots of early inquiry to intelligence. Right? Thanks.
Okay, thank you, E. I think given the time, let's just move right to the discussion as quickly as possible. So just to be a bit clear, the audience, please feel free to post questions on the Q&A box. But I think we're going to kick off some of our conversation just with a few overview questions. So I think one of the things that, let me start by asking, I think this is probably for E. Harry may want to jump in. So the last part of your presentation that was going by rather rapidly was some of the actual implementation and comparison with existing deep learning tools, which wasn't in your original paper. So I assume that you're pursuing that pretty intensively now to try to judge how well this approach is working. Is that right?
Actually, the opposite. We already had those papers out. So we wrote the representation paper based on those based on all the theoretical and empirical results. In fact, I want to point it out. Right, the work started with a work I also did a sabbatical at Microsoft Research Asia, 2007. It started with Harry SHUM. We had a paper tried to using the compression approach to understanding clustering and classification. Right. The roots of that also started at Microsoft Research Asia. Right. As Harry pointed out, many of the roots go back to Microsoft Research.
I see.
I would say, I just add that, and I'm sure there will be more experiments to be done, along the side. And he actually very quickly also went through that, not only the thing that we have done a lot of experiments on supervised learning, and then more and more this incremental learning, self-supervised learning, and there are many projects being planned. But to make those points, in this presentation, E is right that we have done enough experiments to prove those points.
It's for visual data modeling.
Yeah.
So then let me maybe turn this a little bit in a different direction. So one of the advantages that you were emphasizing in going through some of that data is that unlike a lot of these deep learning techniques, the system learns a lot and we don't learn that much. In particular, we don't necessarily know what the features are that, what the classification actually looks like. And you've emphasized here that that's not the case, that you can identify that. So I wonder, to what extent does this approach look like the way learning works in organic systems like primates? So for example, in some of those visual discriminations, you can now say what the network is actually discriminating on. Are those the same kinds of features and the same kind of way things work in the primate brain, for example?
So I can answer on the computational side. I'll let Doris answer the nature side. So in computational side, this you can see this also turned the learning approach a little bit opposite with the current practice. The current practice, human intervened a lot. Human decided what are incoherent, what should be incoherent. And the result is that you end up with something black. Human knows less after learning. Before learning, human think they know more, right? It's impossible. After learning, actually human knows little, what they really actually have learned. This approach is actually opposite, right? In the beginning, actually human make very little assumption. Everything tries to be as autonomous as it gets. Yet in the end, we know the system learned is structured, compact. We actually know more about what the system has learned internally and why it has learned, right? So this is actually, in this case, it's already very, very different, pointing the practice of the machine learning into different directions now. Maybe Doris can comment.
Yeah, I see that as a great advantage. But Doris, maybe you can comment.
Sure. Yeah, thank you. the brain has tons of feedback. Every pair of areas is connected in both feed forward and feedback directions. So I think, it's a fairly good bet that whatever the mechanism for autonomous learning is, it involves some kind of closed loop. But what the details are, is the brain using this white box unrolling scheme that, E beautifully described, or is it using something like backprop? We really don't know, right? In neuroscience, all the studies of learning have been at single synapses. Record from two synapses and I mean two neurons that are connected, and you show this thing called Hebbian learning, right? Where if a neuron successfully causes a downstream neuron to fire, then the strength increases. And I think one of the huge impacts of deep learning for neuroscience has been to show how powerful network learning is, where you have a cost function somewhere many layers down, and if it can somehow affect the weights, systematically dictate the weights of the neurons, many layers earlier on, then you could get this very powerful learning, right? And that's not a question that neuroscientists really thought about until now. Now there are many groups trying to understand what is the mechanism for network learning. That's one of the holy grails right now of systems neuroscience. So we don't know what the primate brain's mechanism is.
I see. That's very interesting. I think part of the question that I was trying to get at, though, is as E has emphasized, that one of the great advantages of the system that you guys have implemented is that it does provide you information, which is absent in many other systems, about exactly what the network focuses on. And I would think that you could do some macro level experiments to decide if that is indeed the way primate brains are working. So for example, in some of the image recognition schemes you showed, it went by quickly, so maybe I didn't fully understand it, but it seemed like you could identify the specific features that the network had identified for discriminatory purposes. And I'm just wondering if there's any evidence for specifically those discriminatory features in, say, human or primate
Yeah, E and I are actively collaborating on that. So we're comparing the responses of neurons in monkey infratemporal cortex to the representations that he's learned with this ReduNet and with other networks, and comparing. So yeah, it's a great question.
I see. Great. That's very interesting. Thank you.
And also, it will be a big challenge is actually to how to really match what the computational system is doing versus what maybe the conditions of the brain, right? So that's actually very exciting things to do in the future. See how this kind of computational framework to some extent it gets also realized in the primate's brain as well. Yeah.
So one of the things that Doris said, which I find very interesting, is that a lot of the neuroscience has focused on in the individual or few synapse range rather than the network as a whole. So one of the things that has been a big theme in physics, for example, is how you can start with simple objects, and the behavior of those simple objects is completely well understood, but when you make a network of them, it behaves in a totally different and often unexpected manner. So one of the questions that I've always had about deep learning itself is whether it's just very effective function fitting, or whether it inevitably goes beyond that. Will we expect to see kind of collective behavior that is different from just scaling of the system larger and larger?
So between discrete domains, maybe the function could be deep network could be a good functional approximator because the function definition is well defined. This is exactly probably the most misleading thing from the very beginning. Many years ago, with Yang LeCun, with Emmanuel Candace, all the harmonic analysis folks, we have discussed this. Deep networks, at least as far as I understand, for modeling visual data, like in this scheme, the F function, is absolutely not a functional approximator. Why? Because this function is not defined at all. So the data you saw, the X, is only available on the zero measure set in the input space. All images in natural images are zero measure set in the space of many dimensions, period. Hence, all the function outside of the support of X is not even defined. Then tells me what function you are approximating. Absolutely not, okay? This is a huge misleading. That's why a lot of early theory about the understanding deep network try to characterize deep network as a class of functional approximator. To me, I think that's very, very misleading, right? The function, the operation of F and G is precisely manipulating the manifolds or the distribution of the data. That's why if you take the rate reduction, right, suddenly you start to see, if you have a measure of the configuration of those, the delta R, the gradient of the delta R is measuring the configuration of those distributions. The gradient are precisely resonate, or if not precise, but at least eerily similar to what each layer of residual network or each layer of transformer is doing. It's doing the hammering, it's forging of the manifold. It's not functional approximation, period, right? Any theory continue to do that, it's fine, right? They can continue to study deep learning as a branch of harmonic analysis, but I don't think they're really matched with what's really deep networks is doing to the real world data.
Interesting. So
I would just add from a very naive perspective, hooking up a bunch of, integrate and fire elements and being able to get like DALI or GPT-3, that seems like a phase transition to me. It seems like something different is happening. I'm not sure anyone would have expected like such behaviors. And maybe that just says that these behaviors are function approximation and they're not that mysterious to begin with. I don't know.
So I think that's a really interesting question. So we don't know, I mean, it is a question, right? It's something that we don't know the answer to, whether even the human brain works in that way or not, whether it's a qualitative difference or whether it is just function approximation is intelligence. Is that, Doris?
Yeah, exactly. I mean, I think Harry started out by bringing the question, what is intelligence? I think that's the question.
Yeah, I just add a little bit here is that E and I were just talking about the recent blog, by Barack at Harvard. And to your earlier question, Andy, that is the deep learning really a function approximating, or is actually learning something different, especially as the number of parameters goes so big. So the phrase that more is different, but why? Mm-hmm. And I think E and I had some very interesting conversation that I think you might want to also elaborate a little bit why you don't think, well, you already said that mathematically it's not even function approximation here, but overall as the number of parameters, as the number of layers goes up so much, and with so much more data, even Doris mentioned earlier that somehow DALI presents you this kind of very interesting results. So it seems like something's happening there when the scale goes up so significantly.
You can, yes.
Yeah, I don't know if you heard that. If you want to say something. Did we lose him?
No, he's there.
Well,
did you want to respond to what Harry just said?
Yeah.
Can you say that question again? Sorry.
Yeah. So I'm saying that we were just talking about this guy, Bose Barack's blog, that is saying that the more is different. Deep learning maybe is different from what people think about. It's just the statistics, and that is this just a function approximation, or is actually learning something that's more explainable there, like teaching students how to do math. So you and I had a little bit discussion there. You really didn't like that analogy of metaphors, and so I just thought you might want to just comment a little bit.
Yeah, I think, see, right now people have a lot of, I think early history about deep learning has generated a lot of folklore about deep learning, right? People start to, everybody take a different perspective or views on how to understand, make analogy. Metaphors are, I think metaphors are great if you already know the truth, and then you explain that to people, right? But the metaphors can be very, very misleading before you know the truth, right? It can become very, very misleading, even wrong, very often, right? Because we don't know the whole picture. Especially in the deep learning, I think the deep network strikes me in my last few years of study. I really start to find a very, very common reason behind the many, many misunderstandings, including some of the top minds in the world, right? Intelligent system is a system. It contains multiple pieces, right? If you look at even that single closed loop, it already embraced the measure is information theory. The deep networks is optimization, right? It's not a function, I still believe, right? The deep network is just doing optimization. It's not approximating any function. And also, the mechanism is through feedback control. And also, control is not enough. There should be a self-critic mechanism to ensure that the data, the model you learn is consistent. Otherwise, you cannot. Everything is actually necessary here. So there's already 4 pieces, right? Let alone there's nonlinearity. There's shift invariance, like what you see that Wiener already mentioned that in his 1948 book, right? Those are the elements he said are essential. He's probably the first person looking at the intelligence from all the pieces. If everybody is like a blind man to an elephant, grabbing one piece, think that is going to explain what intelligence or even learning is all about, I think you're doomed to have all kinds of thinking it's mysteries. Something you cannot explain because you start making metaphors. I think we're beyond that stage now, right? We already know the right methodology is actually we have to unite and build. Put all the pieces together, solve the puzzle. Rather than still everybody think, this is all about information theory, or this is all about deep network. It's just one segment, right? Oh, this is all feedback. No, it's not, right? It's actually all the pieces, all the mechanisms work together to make the learning adaptive, autonomous, and resilient. If you don't miss, if you only, yes, fine, you can do open loop, right? In control, we learned that 70 years ago. We can do open loop control. Everything works. It's only that it's very expensive. Every system we have to invert, do the system ID. Give me a lot of data, give me a lot of computation. We can identify the system. We do open loop control. And then don't expect this works even if the plan changes. Don't expect this to be adaptive. Don't expect this to be robust, right? That's a lesson control people have learned 70 years ago. Somehow we start losing common sense, right? Something lesson we have learned so long ago. Now we're advocating training network, bigger the better, end to end. Despite the neural collapse, despite the mode collapse, and despite the catastrophic forgetting, we somehow just marching with this is the way to success, to final empirical performance. I think there's a bigger lesson to learn from here, right?
Yeah, I think
we have to be.
We mostly agree that the winner is amazing. Yeah, that 70 years ago he had the foresight. So Andy, you probably have some other questions, from audience or others.
Well, we have a few questions. I would say most of the questions from the chat box are rather technical. Maybe I'll try to pick one that's not overly technical. I think, Ian, your talk, one of the starting points was the assumption that you have this very large data space, but that the relevant data tends to live in classes. So the question is it how necessary is it that the data actually be labeled in different classes, and do the representations learned depend on the labeling of the classes? For example, for facial images, suppose you label according to identity versus label according to emotion or some other aspect of the image.
So I think by the way, so all the things actually are, the only thing what's essential is the data has low-dimensional structures, and different classes has separable structures. They don't have to be labeled. I think that's the beginning of all learning, right? As I demonstrated. In fact, the same closed loop, this transcription works even you don't have the labels. All the things that really drives learning or pattern, the learning is really just the data has, different classes has its own low-dimensional structures. That's all you really need, right? The correct label just make that learning, linearization, representation easier, make the optimization easier. Without label, you have to also recover, do the clustering, do the grouping based on the data, based on the features. It's much more complicated process, more challenging problem. Actually, that's a problem that Harry, we set out to do 15 years ago, try to clustering data using compression. So that's that. Another thing is, yes, you can label data differently, which really also means that you maybe learn different representations. However, this framework is already very different from the early success of deep learning, right? It says that we try to do, once I have those labels, how I learn this mapping. So even early theory, like information bottleneck, was developed to try to explain this, right? What the feature gets extracted are most relevant to a class label. But I actually believe this is the wrong way of looking at the problem. Why? How do you know the label is correct? The labels are correct because they are called in accordance to the structure of the data. Label does not change the structure of the data. Structure of data can change labels, right? So as you can see later on, a lot of the learning, we learned attributes like hats, sunglasses. Why they pop up as principal component? Because we didn't ask the system to learn that, because it's those features, those attributes existed in the data, and it shows up with high frequency. The statistics structure of the data make it a component. We humans do not get to stipulate that. So imposing data on the data can be very, very misleading, right? Here, I think the learning to a great extent is trying to learn the structure of the data. So in a sense, our work is really trying to shift our attention back to the structure of the data rather than try to fit the label actively, proactively, right? So that's actually hopefully answer your question, right? The differentiator, this is kind of two views. Our focus is really on the structure of the data. We don't really need a label to begin with. Having label just make the optimization simpler.
Right. Great. I think that was a great answer. I had a question. In terms of, you've made, I think, a pretty convincing case that parsimony and self-consistency are essential ingredients, and you end up with something that doesn't have a lot of knobs that you can twiddle. It's pretty well contained. It seems like the most specific thing that one could argue with is the choice of the rate reduction function for minimization. Are there other? So you had a trade-off between we certainly know the Shannon entropy, but practically speaking, it's not useful because you can't. It's not computationally tractable. So you had to make some compromise, and you identified something that is a good compromise between computability and containing the information that you want. But are there other choices? How unique is this?
I think actually the rate reduction, rate distortion is closely associated with Shannon entropy. All right, it's actually, you can think about it, it's kind of discretized version of it, right? And in fact, to be able to convert any continuous random variable to finite bits, that's something you have to quantify, right? The only thing we introduced there is quantification. Whether or not nature or other quantification makes sense for other say structure, using sphere is a good quantization of absolutely not, right? There could be other, even for communication, right? People can introduce different kind of norm balls to pack for different error correction if they know the distribution of data better, right? So the choice of sphere is sort of the most basic and natural one, but there could be others. That said, but that's just measuring the information per se. But don't forget, here our job is trying to encode the data, right? But any new learning system, just like in our paper, Harry and we have discussed a lot, right? There are also other purpose can be associated with learning, especially when in the reinforced learning. If we are learning not just to learn the visual data to code, to memorize, our job is also to use it to predict, to achieve certain tasks. Then there will be cost associated with utility, or reward, or cost associated with that. Other energy, other forms of cost could get introduced, right? In the recent paper, Yang and Kung also talk about, right? There could be other, if you really start to associate learning with some task, there definitely will be other loss or cost can be introduced. But whether or not they can be as basic, as fundamental as rate reduction, we don't know, right? Maybe in physics, we can measure by energy or action and so on. But if it's something similar to that, associated with, let's say, certain task, reinforced learning, reward design, I think that's still, people are still working on that, right? So we talk a little bit about in our paper, speculate a little bit about how the same closed loop system or game theoretical framework can help us identify those things in the task-driven setting, such as reinforced learning. But it's just speculations.
I see. So in the Q&A box, there are actually quite a few questions which are rather similar. So let me try to combine them. Really, the questions at the heart, I think, are whether this approach is in fact related to how organic intelligent systems actually work. Is this really the approach that the brain takes, the primate brain, for example, or whether artificial intelligence is just something different? So first, that's a question of, do you think that this is likely to be the way the brain works or not? And then I think a more scientific question is, how do we go about telling whether that's the case or not?
Well, that's a question really for Doris, right?
We already touched upon this before, I think. I just want to say personally, like how I got into this. I'm a neuroscientist. I moved to Berkeley a year ago, and I got interested because my lab, has been independently, like extremely interested in what the role of feedback is, right? I just completely independently, I think that feedback is fundamentally important for learning. Like I don't see any other way to do unsupervised learning, because the only training signal the brain has is the external sensory input, right? So yes, so that's why when I started talking to E, and E contacted me because he wanted to talk about his new scheme that could solve the problem of catastrophic forgetting. I went in there quite curious, and then I realized, oh, he's talking about a closed loop here, and the ideas are so similar to the ones that I've been thinking about. And so it's really, and many others, right? In neuroscience, there's many people excited about this concept of predictive coding. So there's so many people interested in this idea of how a closed loop can enable unsupervised learning. So I think, the devil's going to be in the details. How exactly is that implemented? Is the error measured at the final layer, like E and Harry suggest, or is it measured at each layer in a hierarchical chain? Like we have to figure out all of those things. But I think the general picture, the closed loop that enforces self-consistency, I think that's almost certainly going to be a very important element, right? It's a true principle. And then also the second, the principle of parsimony, also really excited me, right? Because I read these papers about how maybe the brain's trying to represent things using the minimum, encoding length, minimum, like what is Kolmogorov complexity, and they seem like they were missing something essential about structure, and how you want representations that you can actually use. And this is exactly what E and Harry were talking about, right? That should be your goal. And so I feel like these two principles that they've identified really are fundamental. That's why I was so excited to be, have the chance to be part of this conversation. But yeah, in the details, is it really a pursuit evasion game between the encoder and the decoder? We'll have to see. And
yes, so I wanted to add just to what Doris, right? So in fact, we just do the joint coding. We didn't even know how many even exciting property about closed loop until we talked to Doris. She's suggesting that, oh, monkey don't learn 10 categories together, right? We do, they don't even do one categories at a time. We just give them one sample at a time. So actually, we went out, we did the unsupervised learning, tested if the network holds up. And this is the recent work. Turns out it actually works. You can, the net group, this closed loop, sample group, closed loop can learn one sample at a time. You don't need any you don't need any labels, right? And this kind of block diagonal structure class, if your data has no dimensional structure, that's all you need. Even the features start to form like subspaces. There's block diagonal structure start to show up. And actually, this is actually joint work with Yang Kun's group. I mean, because of, halfway along the way, his actually students postdoc was using the rate reduction for self-supervised learning. So they heard what we are doing, that we actually could join the force, generated some of those results. Actually, it's quite remarkable. Turns out, and another thing I want to add, Doris, is that you mentioned this game. I actually start to think about this is absolutely important now, right? Not only this framework makes things autonomous, as Andy pointed out, it actually makes it always dynamical, right? See, the current learning is always we train on the data, then we optimize, then we're done, we apply. The learning stops from there. We never stops. We always observe, even we apply our past knowledge to the new instance, we're learning from the new instance. It's always feedback loop. We're always testing how good we're doing with the new instance. So this kind of a closed loop, and also the game constantly put things in checking, right? If my F is good enough, if my G is good enough, even every new instance comes in, it always check the system again, shuffle things around, make sure things gets better, constantly incrementally updating F, G, and the feature space, right? So I can learn, we can even see this, right? We saw something very interesting. Instead of catastrophic forgetting, we see something opposite. If we show the network the data it has seen before, the memory gets better, right? This is the learned airplane in the first round. You see the airplane in the first batch of learning. Then after several classes, we show the network the same set of images of airplane. We found that the feature space for the airplane start to form patterns. The principal components start to become meaningful. Very interesting. It didn't get it in the first round of training. It only get the improved structure after seeing other 10 classes, all come back seeing it again. Just like we memorizing the English words, right? After 1 week, I see the words again, that memory gets reinforced. We see the same kind of phenomena there. It's kind of very, very interesting. But without Doris, we actually never would even try this, right? We'll be happy with our joint learning, right? Compete people with all the scan or generative qualities, right? Publishing papers. But really that she actually asked us to try if the feedback loop works well with this setting, more natural setting. It turns out actually just one surprise after another surprise. And yet we still don't understand the reasons, many of the mathematical reasons behind it. We can only prove the very primitive cases.
Yeah, let me also add to what you said, to kind of sort of bring back a little bit in Andy's question. It's also where I also felt so excited working with Doris to really get this to this principle level that if we look at artificial intelligence, the human intelligence or primate intelligence, that's why we even have this title called the emergence of intelligence. And I'm still struggling to even say, what intelligence really is, for humans like us. Let's say, we have kids. We say when you say, oh, this kid is very smart, intelligent, it's all because he or she can memorize a lot of things. So memorizing things is actually part of intelligence. Then you say the kid can actually calculate very fast. Calculation is really thing. Then later on says the kid can play some games, really well, like connecting 5 things together. Now, if you look at that, AI, computing technology over the last 50 years, one by one, just conquers all the so-called human intelligence tasks. Just be the human, especially with AlphaGo, right? So with AlphaGo, completely, this whole thing is completely out. So now, it's really so intriguing to me is that despite this, probably AI goes one way, like, you have, backprop kind of thing, which is clearly energy inefficient way to do things. Most likely, Doris should really tell us this really not the case. Our brains are probably not really calculating that way. But it accomplishes a lot of tasks so much better than human beings specifically. So those things. But despite that, to me, are there principles, underlying principles, like parsimony and the self-consistency, really working for all kinds of intelligence? And the even more interesting questions that, are there even more principles beyond parsimony and the self-consistency that Yi and I discussed quite a bit? We thought, at least until now, those two are what we can come up with. So that's how, why I think it's so exciting, Andy, look at this space. So much more we can explore.
Well, thank you. I think this has been a very interesting conversation. Sadly, I think that we are approaching the end of our allotted time today. So first, let me thank Doris, Yi, and Harry for agreeing to speak with us today in this way. And let me thank everyone who has been able to attend. I think this is a fascinating subject, very interesting work, and we expect that we'll be having more conversations around these results going forward. So thanks to everyone for joining today.
Thanks, Yi. Thanks, Doris.
Thank you, everyone.
Thanks, everyone.
Thank Harry. Thank Doris. Thank Andy. Thank everyone. If you guys have questions, you can send me emails. All right. Thanks.
Yep.
Andy, I just wanted to, because I love your question about phase transitions. Can I just this is just between you and me.
Yeah.
I think there's when does something become intelligent? Does that involve a phase transition? I mean, I think that's a really,
that's
I don't know how
really interesting question.
How we're gonna answer that, but the ultimate phase transition is consciousness, right?
Right.
How do you go from just inanimate matter to this subjective experience arising? And I really think that this opens up an avenue to study that. If I don't see any fundamental reason why, if we do understand the principles underlying natural intelligence, why we implement them in these GPUs, why they wouldn't become conscious, right? If we did Turing's experiment and wired up a child robot and put it in society, it would learn the way a human baby does, and why wouldn't it become intelligent? And then we can really study the emergence of consciousness in a systematic way that we can't right now. So yeah, I think that question about the phase transition is so interesting.
Yeah. So I think speaking as a physicist, not as a neuroscientist or a computer scientist, that's the fundamental question that I'm interested in. And I think we didn't really have enough time today to go in that direction. But I think what's especially exciting about this kind of development is not so much, and I don't mean to be disrespectful, I'm not suggesting that this isn't the way general intelligence, human or artificial, works, but I think that it's a systematic way to actually start investigating these kinds of questions experimentally. And so in terms of phase transition, so this is something that physicists have been suggesting for many decades, that we are very familiar with phenomena where you take an aggregate of similar components whose behavior you understand completely, and the aggregate then behaves in a completely different way. And there's a technology for describing this, a mathematical language called the renormalization group. I think I mentioned that to you yesterday. And you can't really do a lot of experiments on, or not very convincing experiments on organic systems. There are some people who have tried to do little things like that, like Larry Abbott at Brandeis, who was a physicist, has tried to do some of those things. But having these artificial systems where we can actually do the experiments, but then I think we need the neuroscience guidance to know exactly what we should be trying to measure. So I think that's what's really exciting here. Honestly, I think the work is great, but I'm more excited by the collaboration than I am by the work. Is getting a great neuroscientist talking to the deep learning people, and I think that's what's really exciting here, if I may say. So we still seem to have an audience, which I guess is okay. But Doris, so I would really like to continue this conversation, especially about phase transitions, about deep learning and the like. And so I'm hoping that we can arrange to chat sometime. Maybe we can get you to come and visit once quarantine arrangements tend to relax a little bit. We'll have Harry here at the same time. I gather the two of you have never met in person.
It would be great to have Doris visit us at IAS. I can tell you it's a wonderful environment here, and it would be great to have you visit us in Hong Kong.
Oh, thank you. I'd love to come.
Okay.
Great.
Yeah.
So,
It's a lot of fun.
Then again, to all those audience members who are still here, this has been a lot of fun. I hope that we have more events like this. And Doris, you'll be hearing from me in a day or so by email.
Wonderful. Thank you so much.
So
Okay,
thanks again
bye.
for participating.
Thank you.
Okay, thanks everyone.